class we have derived the equation for expression for buckling load or crippling load of the column when both the ends of the columns are fixed, correct, in the previous class. Okay, we have left with one more derivation, the last derivation. With the end condition, one end of the column is fixed and another end of the column is hinged, correct. So till now we have completed total 3 different derivations with different end conditions till now. Just a minute. Okay. We have completed total 3 different derivations. First derivation is with end condition, both the ends of the column are hinged. Okay, both ends hinged. And next derivation is one end fixed and another end is free. Third derivation is both the ends of the column are fixed. Okay. The fourth derivation for buckling load of the column is one end of the column is fixed and another end is hinged. Okay, for that condition we will derive the equation for crippling load or the buckling load. Okay, you write the headline as expression for, right, expression for buckling load or the crippling load when one end of the column and one end of the column is fixed and other end is hinged. Okay, for this condition we will derive the equation for buckling load. Okay, write that as expression for buckling load or the crippling load of the column when one end of the column is fixed and other end is hinged. Okay, now I'll write the figure for the same condition. I'll write the figure. See, one end is hinged and other end is fixed. Okay, draw a column with dotted line. So original alignment of the column will be straight, that you write it by dotted line. Okay, original alignment of the column will be straight only, that you write by dotted line, and deflected form of the column you write by solid line. Okay, now I will give fixed support to the one end of the column. I will give fixed support to the one end of the column and hinge at the other end of the column. Okay, hinge at the other end of the column. Now, due to the force P applied or the buckling load P applied to the column will undergo deformation. What kind of deformation? See, as we are provided hinged support here, at the hinged support the rotation will be allowed. Okay, at the hinged support the rotation will be allowed or bending will be allowed. But on the other side, we have the fixed support. At this fixed support, there won't be any rotation of the column. Okay, now I will write the deflected form of the column. So this is the deflected form of the column, students. Okay, see here we are provided with hinge. Rotation is allowed, but here we have fixed support. There won't be allow of rotation at the fixed end. Okay, so this is what the deflected shape of the column when one end is fixed and another end is hinged. Okay, now I request all of you to practice parallelly. You need to write the things which I am writing parallelly so that you will understand in a better way. Now here we have the fixed end, correct? Here we have the fixed end. As I said, the rotation will be restricted at the fixed end, correct? The rotation will be restricted at the fixed end. Therefore, there will be fixed end moment which induces at the fixed support. Okay, what kind of moment? Fixed end moment. So what will be the nature of rotation here? Column rotation, it will be like this, means clockwise rotation. So for this clockwise rotation of the column, there will be anti-clockwise reactive moment induced at the fixed support, as like previous case. Call this as M0. Call this as M0. Okay, for this rotation at the fixed support in clockwise direction, there will be anti-clockwise reactive moment M0 induced at the fixed support. Okay, and there won't be any reactive moment at the hinged support because it will allow the column to rotate. That is why it will allow the column to rotate. That is why there won't be any reactive moment induced at the hinged support. Only the moment will be induced, the reactive moment will be induced, or the resisting moment will be induced only at the fixed support. Okay, you can see the same thing in the previous derivation. Wherever we have the fixed support, there we will get the resisting moments. Here you can see in the third derivation whatever we have done. I think here it is there. Yes, here here you can see both the ends of the column were fixed. So wherever the fixed support is there, there you will get the reactive moment like this, M0. Okay, so here we have fixed support on only one side of the column. Therefore, the reactive moment or the resisting moment will be there at only one side of the column where the fixed support is provided. Okay, now you can see that the resisting moment will be developed here, and this resisting moment should be counterbalanced to maintain the equilibrium. Okay, whatever that resisting moment induced at the support, it should be counterbalanced to maintain the equilibrium of the column. For that, at hinged support, there will be reaction induced H. Let us call it as H. Okay, it will be horizontal. Okay, so to counterbalance this resisting moment or to maintain the equilibrium, a horizontal thrust will be induced at the hinged support. Okay, so similarly, as like the previous derivations, you need to consider a section. You need to consider a section at a distance x. You need to consider a section at a distance x from the bottom support. Okay, let y be the deflection at a section X. Let us call this point as D. Point on the column as point D. Okay, it is same for all derivations, correct? Consider a section of the column at a distance X. Okay, and corresponding displacement I have assumed as Y. Okay, at a distance X. Okay, so all of you understood up to here, students? All of you understood? Because Moksha, Bharat.
Yes, sir.
Okay.
Yes, sir.
Now, okay. Now I will move on to the actual derivation part. Here also we have to follow the same procedure whatever we have followed for the previous cases or previous derivations. Okay. Initially we have to take moment about D. Okay, moment about D. Before that I will write let P be the crippling load or buckling load. 100% there will be one particular derivation asked in your examination. If you prepare for all these 4 derivations, 8 to 10 marks will be in your hand. Okay, crippling load or buckling load for which the column has just buckled. Okay, let P be the crippling load or buckling load for which the column has just buckled. Okay, now taking moment about D. Okay, taking moment about point D or taking moment at section X point D, what you will get? M is equal to moment M is equal to, okay, you find sum of moments of this force P and H about point D. Okay, so what is moment of this force P? Moment is nothing but force into distance, force into perpendicular distance. Force is P, and perpendicular distance is, how much is the perpendicular distance? Y is the perpendicular distance. Okay, perpendicular distance of point D from line of action of force P. See here we have the line of action of the force P, means this dotted line itself the line of action of force P. Okay, from that line of action of force P, D distance distance of point D we need to measure. Okay, so Y is the perpendicular distance for line of action of force P. So P into Y. P into Y. What about the sign plus or minus it is? See, the deflected shape of the column, it is concave form, correct? It is in the form of concavity. So the sign is negative. Or else you can decide the sign based on the direction of the rotation of this force P about point D. How this force P will tend to rotate the column about point D? See, you just observe this. Here we have the line of action, downward direction. Here we have the point D. About point D, this force is tending to cause the anti-clockwise moment, therefore negative sign. Or just you can decide that because of this concavity you can directly write minus P into Y. Now moment of this force P about point D is over. Then similarly you take moment of this horizontal thrust about point D. Okay, take moment of this horizontal thrust about point D. So H into what is the perpendicular distance of horizontal thrust about point D, students? See, here we have the line of action of force. So this is the line of action of force. We want perpendicular distance of this point D from line of action. So if we take L as total length of the column, what about this distance? From here to here, X, total length is L. Okay, if you want to get distance between the horizontal thrust H and the section where you considered, so it will be how much? It will be L minus X, correct? L minus X. So the moment of this horizontal thrust about point D will be H into perpendicular distance, okay, of the point D from line of action of the horizontal thrust is L minus X. H into L minus X. What about the sign plus or minus here? Plus or minus? About point D, this horizontal thrust is tending to cause clockwise rotation. So the sign is plus. So plus H into L minus X. So sign is plus H into L minus X. Okay. And we know that the same moment or the generalized equation for the moment is given by EI into what? EI into d square y by dx square. Okay, this is second step is similar for all the derivations. You can see. We know that m is equal to same equation I written here. M is equal to EI into d square y by dx square. Okay, so from both the equations, from equation 1 and from equation 2, you can write as EI into, therefore EI into d square y by dx square is equal to minus py plus h into L minus x. Okay. Now, what next, students? After this, you need to segregate the y terms on one side of the equation. What I will do is I will take this py term to the LHS. So I will get it as EI into d square y by dx square plus p into y is equal to h into L minus x. Okay, this step is also same for all the different cases. You need to segregate the y terms on one side. After this, what is next step? Again, dividing by EI on both sides. If you divide the whole equation by EI on both sides, what you will get? You will get d square y by dx square plus p by EI into y is equal to h into L minus x whole divided by EI. Okay, this is what the equation you get. Okay, what is next step after this, students? What is next step after this? Now you got the equation, quadratic equation with variable y. So to write the solution for this equation, in the RHS part, no, in the RHS part, whatever the coefficient of y we have, that is p by ei, in the RHS we should have the same coefficient in the RHS. Okay, so to get the same coefficient in the RHS, what we have to do? We have to divide and multiply by p, correct? We have to divide and multiply by p. What I will do, for the same RHS, I will multiply by p and divide by p. Okay, I will multiply by p and divide by p. So if you simplify equation in that manner, that is, whatever the coefficient of y term you have in the LHS, same coefficient if you get here in the RHS, you can easily write the solution of the equation. That is why even in the previous derivation we have multiplied and divided by p. Even in this derivation also we have to do the same thing. Okay, so it becomes d square y by dx square plus p by ei into y is equal to, what is the required term for us? P by ei. I'll write first p by ei into remaining term is h into L minus x whole divided by p. Okay, h into L minus x divided by p. Now it is in the form of d square y by dx square plus p by ei into y is equal to the same coefficient we have, p by ei into, we have some constant, multiplication constant for this p by ei term. Okay, now the solution of the above equation, differential equation, is, therefore the solution of the, am I audible, students? Am I audible?
Yes, sir.
Okay, the solution of the above quadratic or differential equation, the solution of the above differential equation is, you will have the same kind of solution as like the previous derivation, that is y is equal to what solution we had in the previous case? I will just go through it. See, the solution of the above differential equation, this term is common for every derivation. This term is common for every derivation. Only the right term will change. Right term will be decided based on coefficient of this p by ei. So in the third derivation, where both the ends of the column were fixed, the coefficient of the p by ei was m naught by b. That is why we have written plus m naught by p. Okay, this term will be the same. Okay, this term will be the left term will be the same. That is c1 cos x root p by ei plus c2 sin x root p by ei will be the same, plus coefficient of p by ei in the RHS we need to write. So that will be the solution for the equation. Okay, now similarly I'll write the solution for this above equation. It will be c1 cos x root p by ei plus same c2 sin x root p by ei plus what will be this third term, students? Whatever the coefficient we have for this p by ei in the RHS, that will come here. That is h into L minus x divided by p. That's it. That is how we write the solution of the equation. Okay, only you need to remember this term. If you remember the third term, you can write just by looking into the coefficient of p by ei in the RHS. That's it. Okay, now you call this as equation number 1. Call this as equation number 1. Okay. Now we have written the solution of the equation. This is the first step. Second step is to apply the boundary conditions to get the constants of integration C1 and C2. Okay, below write a sentence. Below write a sentence where C1 and C2 are the constants and are obtained by boundary conditions. And are obtained by applying boundary conditions. Now we have to apply the boundary conditions. Before applying, we will write what are the boundary conditions will come for this particular case. Okay, now write the sided line as boundary conditions. Write the sided line as boundary conditions. Now, how to write the boundary conditions? By just looking into this type of support. Okay, by just looking into the type of support, we have to write the boundary condition. Here at the bottom of the column, we have the fixed support. For fixed support, okay, means at x equal to 0. Okay, at x equal to at the fixed support x equal to 0, correct? At x equal to 0 means at the fixed support at x equal to 0, deflection y is equal to 0, correct? There is no deflection here. This y is 0 at the support when x equal to 0. We will get one more condition, that is dy by dx equal to 0. And slope of the curve dy by dx is also equal to 0 at the fixed support. Remember, always at the fixed support, this condition will apply. At x equal to 0, y equal to 0 and dy by dx equal to 0. Even in the previous case, we have got the same boundary condition. Here you can see. Even at the top and bottom. Okay, at the bottom at x equal to 0, y equal to 0 and also dy by dx equal to 0. And here in this case, we have fixed support on both the ends of the column. Even second boundary condition was also same. For fixed support, you need to remember this. Similarly, for hinged support, okay, for hinged support, which means that at x equal to L, second boundary condition I will write now. Second boundary condition at x equal to L, y equal to how much? It is 0 only. There is no deflection. At x equal to 0, y equal to 0. Okay, this y value is equal to 0. Similarly, at x equal to L, at this point, at hinge point, at x equal to L also y equal to 0. But dy by dx is not equal to 0. There is some slope here. Dy by dx is nothing but slope. Okay, there is some slope here. Here we have some slope. But here we don't have the slope. We have the straight vertical line. Okay, that is why the dy by dx equal to 0, it will not come. For hinged support, only one condition will come, that is y equal to 0, displacement equal to 0. Okay, now what we will do in the next step, utilizing these boundary conditions, we will find the values of constants C1 and C2. Okay, now I will take the first boundary condition. First boundary condition, that is at x equal to 0, y equal to 0 and dy by dx equal to 0. First I will take this condition. First part of the first condition I will take. Okay, I will take the first part of the first boundary condition. What is that first part? At x equal to 0, y equal to 0. Now in this equation 1, you substitute x equal to 0 and y equal to 0. Let's see what we will get after simplification. Okay, so y equal to 0 y equal to 0 is equal to c1 cos x root p by is there. So x is nothing but 0 only, c1 cos 0 plus c2 sin x is nothing but there 0 will come, it becomes sin 0 plus h into L minus x whole divided by p. Okay, simplifying, further simplification, we get 0 is equal to c1 cos 0 is cos 0 value is 1, c1 plus c2 sin 0 value is 0 plus h into L minus x divided by p. Okay, therefore you will get the value of c1, that is c1 is equal to minus h into L minus x whole divided by p. Okay, by this you got the value of c1. c1 is equal to what? Minus of this constant. That's it. Minus of this constant, you will get it as c1. Similarly, in the previous case, you constant was m0 by p. You got the value of c1 as minus of m0 by p. In this derivation, we have the constant as h into L minus x divided by p. You will get the value of c1 as minus of h into L minus x divided by p. Similar. Okay. Now I'll take second part of the first boundary condition. Second part of the first boundary condition is at x equal to 0, dy by dx equal to 0. Okay. Taking or else first you want the value of dy by dx, no? Dy by dx. We have the equation for y, but you want the dy by dx equation. For that you need to differentiate this equation with respect to x. Okay, differentiate, you write below, right? Differentiate equation 1 with respect to x. So it becomes dy by dx is equal to, okay, dy by dx is equal to, you differentiate this c1 cos x root p by a, it becomes minus c1 sin x root p by ei. Again further differentiation of this bracket term, so it will be root p by ei. Okay, one differentiation of the first term is over. The differentiation of the second term will be c2 sin x root p by is there. It will be c2 cos plus c2 cos x root p by ei plus into differentiation of bracket term will be root p by ei, and differentiation of the third term will be what? Here we have h into L minus x divided by p, correct? H into L minus x divided by p term we have. I'll write at the separate column. We have h into L minus x divided by p, third term. Okay. Now, if you split this equation, it becomes hl minus hx divided by p. Okay. Again, rewriting, it will be hl by p minus hx divided by p. If you split this equation, so this is what the final term you get. So differentiation of this term with respect to x, so this will be a constant. Differentiation of this constant will be 0 minus h by p into x is there. Differentiation of this term will be minus h by p. Okay. So the final answer will be minus h by p. Final answer will be minus h by p. Understood, students? Differentiation of this third term. Third term I have written separately here for make you understand h into L minus x divided by p. Okay. First I multiplied this L minus X term with the H. Okay, by that I got it as HL minus HX whole divided by P. Now I split the equation. After splitting up, what I got is HL by P minus HX divided by P. Okay, now I have differentiated. Okay, differentiated. After differentiation, the differentiation of this constant will be 0. Differentiation of this Hx by P is H by P minus H by P. So my answer will be here how much? It will be minus. It will be minus H by P. Minus H by P. Okay. Minus H by P. Now we have now we will utilize the second part of the first boundary condition. Okay, second part of the first boundary condition is at x equal to 0, dy by dx equal to 0. We will substitute x dy by dx equal to 0. X equal to 0 and dy by dx equal to 0 in above equation. I'm utilizing second part of the first boundary condition. So dy by dx equal to 0 is equal to minus c1 sin x 0 plus c2 cos x is there, c2, it becomes c2 cos 0 minus h by, sorry, I left one more term here, minus h by p, okay. C2 cos 0, here this term is missed, no? This term is missed. Okay, C2 cos 0 into root p by e is missed. I'll rewrite the equation. So this constant is missed here into root p by ei, okay, minus h by p as it is, minus h by p. Okay, now you take this minus h by p to the other side of the equation, that is it becomes h by p is equal to c2 cos 0 value is c2 only, cos 0 value is 1, it becomes c2 root of p by ei. By this you will get the value of c2, therefore c2 is equal to h by p into, if you take this root p by ei to the LHS, what it becomes? It becomes reverse. Root of, instead of p by ei, it becomes ei by p. That's it. Ei by p. It becomes ei by p. So by this you got the value of C2. So here we had two constants C1 and C2 in this equation 1. So we got the values of both C1 and C2. Now you substitute the values of C1 and C2 in equation this in this equation 1. Okay, therefore substituting the values of C1 and C2 in equation 1. So it becomes y is equal to C1 is what? Minus h into L minus x by p. Y is equal to C1 is minus h into L minus x whole divided by P cos x root P by EI plus C2 sin plus C2 value is H by P root of EI by P. C2 sin x root P by EI plus we have one constant along with the equation 1. What is that? H into L minus x divided by P. H into plus H into L minus x divided by P. Call this as equation number 2. Call this as equation number 2. Now we have left with one more boundary condition, that is second boundary condition at x equal to L, y equal to 0. Okay, second boundary condition, all right. Second boundary condition at x equal to L, y is equal to 0. Okay, now applying the second boundary condition for equation 2. Okay, applying second boundary condition, that is at x equal to L, y equal to 0 for equation 2, what you will get, let's see. Okay, substitute, or therefore the equation 2 becomes y equal to 0 is equal to minus h into L minus x equal to how much? L only. L minus L divided by P cos L root P by I plus h by P into root EI by P sin L root P by EI plus h into L minus x is nothing but L divided by P. L minus L becomes 0. So this term becomes 0. Okay. Now you take this term to the LHS. It becomes again here this term becomes equal to 0. No. This term becomes equal to 0. L minus L. Just a minute. At x equal to L, equation 2 will be C1 value is how much? Minus h into L minus, just a minute. So here something, the value of C1, actually I got it as minus h by P into L. Let me check it. C1 value. Yes, definitely you will get it as 0. Here x value is 0, correct? I did not substitute the x value as 0 here. Let me substitute here. X is nothing but 0 only here. It is L minus 0. L minus 0. Or this term I will remove. Okay. So while substituting x equal to 0. So here I have not substituted x equal to 0. That's why I have taken forward the value of x. So L minus 0. So h into L by P. That's it. H into L by P. Okay, h into L by P. So this term is here minus HL by P. Minus HL by P. Okay. So C1 is here minus HL by P. I'll just rewrite it as minus HL by P. minus HL by P. Okay. Minus HL by P. Minus HL by P. Now you take this term to the RHS, it becomes plus HL by P cos into L root P by EI is equal to H by P into sin L is there. H by P into root EI by P sin L root P by EI. Okay. Now on both LHS and RHS, H by P is the common, correct? On both LHS and the RHS, H by P is the common. Just strike off H by P on both LHS and the RHS. Okay. Therefore, root EI by P. Okay. Root EI by P okay. Now you take this cos to the RHS and root EI by to the EI by P to the LHS. It becomes root of P by EI root of P by EI P by EI root of P by EI. Okay, what I have done? I have taken this root of P by EI to the LHS into L. Okay, here we have one term L is equal to you take this cos term to the RHS is equal to sin L root P by EI divided by cos L root P by EI. Okay, therefore the equation becomes here L root P by EI is equal to tan L sin by cos is tan L root P by EI. Okay, it becomes tan L root P by EI. Okay, now the solution of the above equation, the solution of the above equation is, you need to remember this, L root P by EI is equal to 4.5 radians. 4.5 radians. Okay, you need to remember this term, students. So if you find the solution of this particular equation, what we'll get is L root P by EI is equal to 4.5 radians. The squaring on both sides. Just hold for 2 minutes. I'll complete these derivations and you can join for the next class. Squaring on both sides. What will get? L square P by EI is equal to 4.5 square. If you do, approximately you will get it as 20.25. Okay, you will get approximately 20.25. Therefore, the equation for P, crippling load, will be equal to 20.25 EI divided by L square. Okay, but the value 20.25, but the value 20.25 is equal to, approximately it is equal to the value of 2 pi square. you can check it out in the calculator. Okay, you can check it out in the calculator. 20.25 value will be approximately equal to 2 into pi square. So instead of 20.25, I will substitute 2 pi square. Therefore the above equation becomes P is equal to 2 pi square EI divided by L square. Okay, 2 pi square EI by L square. So this is what the final equation for crippling load or buckling load of the column with one end is fixed and another end is hinged. Okay, so with this I'll stop the class to here.